There are objects in the universe that announce themselves with light. And there are objects that sit behind the light, shaping it quietly, forcing it to take longer paths, to arrive redder than it left, to curve around corners it shouldn't be able to see. A neutron star is not a place you go exactly. It's a boundary condition, a set of numbers that refuses to compromise. Mass that stays, radius that won't grow, gravity that makes time, and light behave like careful paperwork instead of free improvisation. It is what you get when a star runs out of negotiation. And tonight, we'll follow the evidence gently, not for exhibition, but for clarity, one calm detail at a time. Good evening. My name is Madeline Rowe, and this is the science of neutron stars for sleep. And if you'd like to keep drifting off with calm, evidence-based case files, please feel free to subscribe. New episodes arrive every other day. Back in my office, it is quiet. A small desk lamp pools warm light across a folder with a simple label, neutron stars. The room is ordinary in every way, except the feeling that everything inside it has been arranged to save space. Books are shelved tight, pages pressed flat, notes clipped and layered, gaps eliminated. Even the air feels a little denser near the desk, as if the room has learned a trick, how to hold more than it should without looking crowded. That, in miniature, is the neutron star's specialty. We begin with the simplest description, the one that fits on a single line and still manages to feel impossible. A neutron star can pack up to about twice the mass of our Sun into a volume the size of a city. It is the highest stable density we can directly observe. A black hole may be denser in some deeper sense, but it hides the details behind an event horizon. A neutron star does not. It leaves evidence at the surface, in the light it emits, in the way that light bends, in the timing of pulses that arrive as steadily as a heartbeat. If you want a physical image that is both absurd and useful, NASA offers a simple one. A sugar cube-sized piece of neutron star material would weigh around 1 trillion kilograms on Earth, about 1 billion tons, about as much as a mountain. It's not that you could ever pick it up. It's that the number gives your intuition something to hold onto. And once you have that number, the rest of the story starts to feel less like fantasy and more like an investigation into consequences. If matter is that dense, what holds it up? If gravity is that strong, what does it do to time and light? If the star is so small, how do we ever find it? If it spins, how fast can it spin before it tears itself apart? If it has a magnetic field, how intense can it get before it stops behaving like a field and starts behaving like a machine? These are the questions that return again and again in neutron star science. They are not rhetorical. They are measurable, at least in pieces. And the art is learning which pieces can be trusted and which are still uncertain. So we'll move the way you move through a careful report, from the outside in and then back out again. We'll start with what a neutron star looks like to an astronomer who cannot touch it, cannot sample it, cannot place a probe in orbit around it for a close look. We'll start with what arrives at a telescope, photons and timing, spectra and pulses. Then we'll step backward in time to the moment of birth, when a massive star's core collapses, when electrons and protons are forced into new arrangements, and neutrinos, nearly weightless, nearly indifferent, carry away the bulk of the energy. Then we'll return to the present and peel the star in layers: atmosphere, ocean, crust, inner crust, and core. We'll talk about neutron-drip, the point at which nuclei can no longer keep their neutrons caged. We'll talk about the strange intermediate geometries of matter, sometimes nicknamed nuclear pasta, where the competition between nuclear attraction and electric repulsion forces matter into shapes that sound like a menu, but behave like a condensed matter laboratory no one can build. And we'll keep one steady thread running through all of it: the equation of state, the relationship between pressure and density, energy and composition, the quiet rulebook that decides which neutron stars can exist, which collapse further, and what their radii must be for a given mass. Finally, we'll step outward again to the magnetosphere, the region where fields and plasma write glowing signatures around the star, and we'll follow that outward path all the way to the final, most dramatic experiments: mergers. The last milliseconds before two neutron stars collide, when magnetic circuits rewire in real time and high-energy light is created in places it may not be able to escape. That is the map. Now we can begin. The first clue is scale. Neutron stars are small, and they stay small. Typical values you will see, always with uncertainty, always with context, are masses around 1 to 2 solar masses and radii around 10 to 14 kilometers. A sphere the width of a city, carrying the mass of a star. When you compress mass that far, general relativity stops being a subtle correction and becomes the framework. The compactness of the star, how close its radius is to its Schwarzschild radius, reaches into the tens of percent. That matters because it changes everything about how the surface appears to us. Light climbing out of the gravitational field loses energy. Its frequency shifts down. Its color reddens. Time itself runs differently near the surface than it does far away. And the paths light takes are bent, so that an observer can sometimes see more of the star's surface than Euclidean geometry would allow. This light bending sounds poetic, but it is one of the most practical aspects of neutron star measurement. If the star has bright regions, hot spots, then light bending determines how those spots appear and disappear as the star rotates. And if you can model that appearance accurately, you can constrain the star's size. This is the modern strategy in one sentence. Use the star's own rotating surface features, filtered through relativity, to infer its radius. But before we get to modern instruments, we should ask how neutron stars were ever found at all. For decades after they were proposed, neutron stars were almost pure theory. They were expected to be compact, dark, difficult. Their surface area is small, which makes them faint at the distances of stars. They do not shine from ongoing fusion. Most of what they have is residual: heat from formation, rotational energy, magnetic energy, and sometimes accretion energy if they steal material from a companion. They are not generous sources of visible light. They prefer X-rays and radio pulses and occasionally high-energy flares. And until astronomy learned to listen in those bands, neutron stars were easy to miss. Then, in 1967, something began to beep. Astronomers detected very regular radio flashes. They were too regular to ignore and too strange to place. For a brief moment, there was playful speculation about alien signals, a nickname that lingered: little green men. The explanation, of course, was not alien. It was rotational, a compact object sending out beams that swept across Earth like a lighthouse. This was the moment neutron stars stepped out of theory and into observation, not as a photograph, but as a rhythm. A pulsar is, at its core, a rotating neutron star with a magnetic axis not perfectly aligned with its rotation axis. Charged particles accelerate along field lines, radiation beams outward, and as the star spins, the beams sweep through space. If one of those beams crosses our line of sight, we see a pulse. And because neutron stars are rigid, compact, and rotating with enormous angular momentum, their pulses can be extraordinarily stable. Stable enough that their timing becomes a tool for physics, navigation, and tests of gravity. NASA's Neutron Stars Are Weird article uses a playful comparison. The fastest known pulsar spins 43,000 times every minute, about twice as fast as a typical household blender. It is a funny image, and it's useful because it reminds you that this is not a slow astronomical clockwork. It is fast, compact rotation under extreme gravity, with the star's surface moving at a substantial fraction of the speed of light. So we have our first solid evidence, periodic pulses, something small and massive rotating quickly. But a pulse is just an announcement. The deeper question is what a neutron star is made of and how it came to be. To understand the birth, we return to the precursor, a massive star's core at the end of fusion. A normal star lives in a balance between gravity pulling inward and pressure pushing outward. For most of its life, that outward pressure is maintained by fusion, by the heat of nuclear reactions. But fusion is not a perpetual engine. It depends on fuel and on the energy balance of reactions. In the cores of massive stars, fusion progresses through stages. Lighter elements fuse into heavier ones, releasing energy, until you reach iron group elements. Iron is special because, at the conditions inside a star, fusing iron into heavier nuclei does not release energy. It costs energy. Iron is, in a sense, a dead end for energy-producing fusion, so the star's core accumulates iron. It grows. It becomes supported more and more by degeneracy pressure rather than thermal pressure, especially electron degeneracy pressure. Degeneracy pressure is one of the universe's quieter rules. It comes from the Pauli exclusion principle. Certain particles cannot share the same quantum state. Pack electrons into a small volume, and they are forced into higher and higher momentum states. That momentum creates pressure, a resistance to further compression. A white dwarf is supported primarily by electron degeneracy pressure. A neutron star is what happens when even that is not enough. When the core's mass passes a threshold, often described with the Chandrasekhar limit as a reference point, the core can no longer be supported by electron degeneracy pressure alone. Collapse becomes inevitable, and collapse is fast. It is not a leisurely contraction, it is a catastrophic inward rush. As the core collapses, the density rises, temperatures rise, photodisintegration occurs. High-energy gamma rays break iron nuclei into smaller pieces, a process that consumes energy and removes pressure support. This helps the collapse continue. Then comes a reaction that changes the star's identity. At sufficiently high densities and energies, electrons are forced into protons. Electron capture turns protons and electrons into neutrons and neutrinos. The reaction is simple to write and profound to live through. A proton plus an electron becomes a neutron plus an electron neutrino. This process, neutronization, reduces the number of electrons available to provide degeneracy pressure, which makes collapse easier. It also produces a flood of neutrinos, and neutrinos matter. Most of the gravitational energy released during core collapse leaves the star as neutrinos. The number often quoted is on the order of 10 to the 53 ergs, an enormous sum, with only a small fraction going into the kinetic energy of the exploding envelope, and a smaller fraction into electromagnetic light. Neutrinos are famously elusive. They rarely interact with matter. In the early stages of collapse, neutrinos can escape, carrying away energy and lepton number, draining the core further. But as densities climb high enough, neutrinos can become trapped for a time within the collapsing material, and the details become complicated, details that depend on neutrino transport, opacity, and the evolving structure of the proto-neutron star. The broad story remains: the collapse produces neutrinos, and neutrinos carry away much of the energy. The newly forming neutron star is born extremely hot, with temperatures around 10 to the 10 or 10 to the 11 Kelvin in the earliest moments. Then it cools, first very rapidly, primarily through neutrino emission from the interior, and later more slowly through photons emitted from the surface. At a critical density, near nuclear density, the density of an atomic nucleus, the collapse halts. It halts because matter becomes nearly incompressible on nuclear scales, and because neutron degeneracy pressure and strong force repulsion provide a fierce resistance to further compression. The inner core rebounds, a shock wave forms. Whether that shock successfully blows off the star's envelope in a supernova is one of the deep problems in stellar astrophysics, involving neutrino heating, convection, and instabilities. But in cases where a neutron star is left behind, the result is a compact remnant, a proto-neutron star that settles, cools, and becomes the object we observe. So that is the origin: collapse, neutronization, neutrinos, bounce, remnant. Now, with that birth in mind, we return to the present and examine what is left. A neutron star is often described as layered, not because it is neat, but because the physics changes with depth. The outermost layer, in the strictest sense, is an atmosphere, a thin plasma where the star's thermal radiation spectrum is formed. Depending on temperature and gravity, that atmosphere can be millimeters to centimeters thick, sometimes even thinner. It can be hydrogen, helium, carbon, or more complex mixtures depending on the star's history, what it was born with, what it has accreted, what has sunk. Under the atmosphere is sometimes described an ocean, a liquid layer of ions and degenerate electrons, a Coulomb fluid under extreme gravity. And beneath that is the crust, a solid lattice of nuclei embedded in a sea of electrons. The names, atmosphere, ocean, crust, sound familiar because they borrow from Earth language, but the physics beneath them is not Earth-like. The key idea is that, at these densities, electrons are highly degenerate and often relativistic. They provide a significant portion of the pressure in the outer regions. Nuclei arrange themselves in a lattice because the energy is minimized that way. Electrostatic interactions balanced in a crystalline structure. It is, in a sense, a white dwarf-like material pressed into a much smaller radius by stronger gravity. As you move deeper, pressure rises. The equilibrium composition of nuclei changes. Nuclei become more neutron-rich because the environment favors it. On Earth, such neutron-rich nuclei would decay quickly. Inside a neutron star crust, they can be stable, and eventually you reach a threshold with a name that sounds almost gentle: neutron-drip. Neutron-drip is the density at which nuclei can no longer hold onto all their neutrons. The neutron chemical potential rises as density increases, and at a point around a few times 10 to the 11 grams per cubic centimeter, it becomes energetically favorable for neutrons to drip out of nuclei and exist as free neutrons in the surrounding medium. From above, you might imagine nuclei as cages holding neutrons. Neutron drip is when the cages start leaking. Below neutron drip, you are in the outer crust. Nuclei in a lattice, no free neutrons, electrons providing degeneracy pressure. Above neutron drip, you enter the inner crust, a region where neutron-rich nuclei coexist with a gas or more accurately, a fluid of free neutrons and degenerate electrons. Under these conditions, the free neutrons can form a superfluid. It's an extraordinary claim, but it follows from the same quantum mechanics that allows superfluidity and superconductivity in terrestrial systems, pushed into a different regime of density and interaction. The inner crust is not infinitely thick. Typical estimates put it on the order of 1 to 2 kilometers, but those kilometers matter. They contain a significant fraction of the star's moment of inertia. They matter for glitches, sudden changes in pulsar spin. They matter for thermal evolution. They matter for how the star responds to tidal forces in a merger. And, in the deeper inner crust, the geometry of matter becomes strange. This is where the nickname nuclear pasta comes in. The phrase is informal, and we should treat it carefully. It is not a claim that we have seen pasta inside a neutron star. It is a description of what nuclear models predict when nuclear attraction and Coulomb repulsion compete under conditions where matter is dense, neutron-rich, and not yet fully uniform. At lower densities in the inner crust, matter can look like roughly spherical nuclei embedded in a sea of neutrons and electrons, droplets in a background. As density increases, those droplets can deform into rods, slabs, and more complex shapes. The classic menu is meatballs, spaghetti, lasagna, and then inverted phases, holes, and tubes, where the roles of nucleus and background swap. The important point is not the food metaphor. The important point is frustration. Two forces with different preferences. The strong nuclear force favours nucleons being close together. The electric force between protons favours separation. In a neutral environment with electron screening charge and with a high neutron fraction, the energy landscape can favour intermediate geometries rather than simple spheres. It is condensed matter physics, but with nucleons under enormous pressure, at densities approaching a significant fraction of nuclear saturation density. And nuclear saturation density is another key threshold, around a few times 10 to the 14 grams per cubic centimetre, or in nuclear units about 0.16 inverse femtometers cubed. It is the characteristic density of nuclear matter inside atomic nuclei. As you approach that density, the distinction between individual nuclei and the background begins to blur. Eventually, nuclei melt into uniform nuclear matter. That is roughly where the crust ends and the core begins. In the core, matter is thought to be mostly neutrons, with a smaller fraction of protons and electrons, and possibly muons. Everything is in beta equilibrium. Weak interactions adjust the composition so that the chemical potentials balance. Neutrons can convert to protons plus electrons and neutrinos, and the reverse. The system finds an equilibrium that depends on density, temperature, and interactions. What lies deeper still, at the highest densities in the core, is uncertain. There are models that include hyperons, pion, or kaon condensates, or deconfined quark matter. There are models that avoid exotic components by having stiffer nuclear interactions. There are observational constraints from the existence of neutron stars with around 2 solar masses, which rule out many very soft equations of state that would collapse too easily. But we will be careful here. The evidence is strongest for the outer layers and for the general fact of a dense core supported by nuclear pressure in a relativistic gravitational field. The details of the inner core composition remain an active area of research. So how do we learn about the core without touching it? We learn through global properties: mass, radius, spin, cooling, magnetic field, oscillations, and, more recently, tidal deformability measured through gravitational waves. The equation of state sits at the center of this whole effort. It is the relationship between pressure and energy density, and it depends on composition. In a normal gas, the equation of state is simple. In neutron-star matter, the equation of state is not just a thermodynamic formula, it is a statement about nuclear interactions. Given an equation of state, you can solve the structure equations of a neutron star. In Newtonian gravity, you would use a hydrostatic equilibrium equation. In general relativity, you use the Tolman-Oppenheimer-Volkoff equation, the TOV equation, which accounts for the fact that pressure itself contributes to gravity and that space-time curvature changes the balance. The result is a mass-radius relation. For each central density, there is a corresponding equilibrium configuration with a certain mass and radius. And for each equation of state, there is a family of such configurations. Change the equation of state, change the family. This is why measuring both mass and radius for the same star is so powerful. If you knew mass and radius precisely, you could eliminate many equations of state and learn about dense nuclear matter in a way no laboratory experiment can. But the difficulty is that neutron stars are small, far away, and surrounded by messy physics in their outermost layers. Atmospheres, magnetic fields, accretion flows, hotspots, and interstellar absorption. So the work becomes a careful disentangling. Mass, in many cases, is measured through binary dynamics. If a neutron star has a companion, another neutron star, a white dwarf, or a normal star, its gravity affects the orbit. Pulsar timing, in particular, can measure masses with extraordinary precision because the pulses act like timestamps. Radius is harder. One traditional method uses thermal emission from the surface, measure a flux and a temperature, infer an emitting area, infer a radius. But even in principle, you must correct for gravitational redshift, distance uncertainty, and atmospheric effects that distort the spectrum. A neutron star is not a perfect black body. Its atmosphere absorbs and emits in ways that depend on composition and magnetic field, and those are not always known. So modern radius work often favours methods that use timing and geometry rather than just spectral shape. This brings us to hotspots. Hotspots can form for multiple reasons. Accretion can heat regions near magnetic poles. Magnetic field geometry can create uneven heat transport through the crust and envelope, producing hot polar caps. Return currents in the magnetosphere can deposit energy. The details vary, but the observational signature is often the same. Periodic modulation of X-ray flux as the star rotates. If you can measure that modulation with high time resolution and good photon statistics, you can model how light bending and Doppler effect shape the pulse profile. A more compact star bends light more strongly, making more of the surface visible at any given time and smoothing out the pulse. A larger star bends light less, producing sharper changes as hotspots rotate in and out of view. This is where NICER enters the story. NICER, Neutron Star Interior Composition Explorer, is an X-ray telescope mounted on the International Space Station. From its vantage point, it studies neutron stars, black holes, and other X-ray phenomena. It also demonstrated a separate, elegant idea, using pulsars as navigational beacons, a kind of cosmic GPS for future deep space missions. But in the context of neutron star interiors, NICER's main value is timing and spectroscopy. It can record X-ray photons with fast timing. It can resolve pulse profiles. And with careful modelling, those profiles can constrain neutron star radii. To make that feel real, imagine the instrument itself. attached to the station, turning in slow controlled motions while the Earth slides beneath. It is a small box of optics and detectors pointed outward at tiny points of X-ray light, listening for periodic signals hidden in a stream of photons. NICER does not see a surface the way your eyes see a sphere. It sees time-tagged X-ray photons arriving with patterns. It sees a waveform, and from that waveform, with enough photons and enough careful modelling, it can infer geometry and compactness. This is not easy. Pulse profile modelling requires assumptions about hotspot shapes, about surface emission patterns, about the star's atmosphere, about the distribution of temperature, about background noise, about the star's spin, and about the observer's viewing angle. It requires general relativity because even the basic mapping from surface to observer depends on curved space-time. But this is exactly the kind of problem neutron stars invite. Hard physics at the boundary of what can be measured. So far, so good. We have the outside-in approach. Now we will slow down and make the inside story feel tangible, because the interior is not just a list of layers. It is a sequence of physical regimes. Begin again at the surface, but this time with gravity in mind. Surface gravity on a neutron star is immense, many orders of magnitude beyond Earth's. One way to express it is in centimeters per second squared, where typical values are around 10 to the 14, depending on mass and radius. The escape velocity can exceed half the speed of light. This has immediate consequences. Anything that falls onto the surface gains enormous kinetic energy. In accreting systems, where a neutron star pulls gas from a companion, that gas can heat to X-ray temperatures as it spirals in, forming an accretion disk and then impacting the surface. Surface irregularities are limited by the gravity. When people talk about neutron star mountains, they may be talking about features inches high. Gravity does not permit tall structures. The surface is forced smooth. And yet, the surface is not simple because magnetic fields can dominate atomic structure. Typical neutron stars have magnetic fields billions to trillions of times stronger than Earth's. Magnetars can be another 1,000 times beyond that. In such fields, atomic orbitals distort. Binding energies change. Hydrogen behaves differently. Matter can become anisotropic, elongated along field lines. So even the outermost layers are already a laboratory in extreme conditions. A thin atmosphere whose chemistry and radiative properties are reshaped by magnetism and gravity. Now step down into the crust. In the outer crust, nuclei are arranged into a lattice, a Coulomb crystal, surrounded by degenerate electrons. The pressure is dominated by electron degeneracy, while nuclear binding energies determine which nuclei are stable at each depth. As density increases, nuclei become more neutron-rich. Electron capture reactions proceed because it becomes energetically favorable for electrons to be captured by protons in nuclei, increasing neutron content and reducing electron fraction. This progression continues until neutron-drip. At neutron-drip, free neutrons appear outside nuclei. A new component is added to the matter, a sea of neutrons that can flow. From here on, the inner crust is a mixture. Neutron-rich nuclei, free neutrons, and electrons. The free neutrons, in many models, form a superfluid. This matters because superfluids carry heat differently, store angular momentum differently, and can participate in neutrino emission through processes associated with Cooper pairing when the star cools through critical temperatures. The nuclei remain in a lattice for a time, but their shapes evolve. Pressure and neutron fraction increase. The environment becomes more and more hostile to the idea of a neat spherical nucleus. This is where pasta-like structures may appear. It is worth pausing here, because nuclear pasta is often presented as a curiosity, but it may have real macroscopic consequences. The geometry and disorder of these phases can affect electrical and thermal conductivity. It can influence how the crust cools after accretion heating. It can influence magnetic field evolution, because electric currents decay differently depending on conductivity. It can influence neutrino opacities in supernova contexts. In mergers, crust properties influence tidal deformability and the detailed response to tidal forces as stars spiral together. Even if the details are uncertain, the theme is solid. The crust is not a passive shell. It is an active player in a neutron star's observable behavior. Then, deeper still, the crust ends. At densities approaching about half nuclear saturation density, nuclei dissolve into uniform matter. The core begins. In the core, the matter is a dense fluid of nucleons, leptons, and possibly additional components. It is in beta equilibrium. It is strongly interacting. It may contain superfluid neutrons and superconducting protons, depending on density and temperature. And because the densities are beyond what we can reproduce in laboratories, the equation of state becomes a synthesis of nuclear theory, many-body calculations, and constraints from astrophysical observations. This is the heart of the unsolved problem NASA highlights, the nature of matter at the highest stable densities we can observe. Now, an important shift in pacing. Whenever we talk about the interior, it is tempting to imagine it as static. But neutron stars are not static objects. They evolve, they cool, they spin down. Their magnetic fields evolve. Their crusts crack and adjust. Their superfluid components exchange angular momentum. Their surfaces change as accretion deposits new material or as bursts eject particles. So we'll take a quiet detour into time. A newborn neutron star is extremely hot. In the earlier stages, its cooling is dominated by neutrino emission from the interior. Neutrinos carry energy away efficiently because they can escape from deep layers once the star becomes transparent enough to them. This stage is fast compared to human intuition about stars. The star's internal temperature drops dramatically in a relatively short time. After the early neutrino-dominated cooling, the star enters a longer era where photon emission from the surface becomes more significant. Surface temperatures can remain in the hundreds of thousands to millions of degrees for a long time, which means the star emits primarily in soft X-rays rather than visible light. The details of cooling depend on many factors. The composition of the core determines which neutrino processes operate. Some processes are slow, some are fast. If direct Urca processes operate, rapid neutrino emission channels, they can cool a star much faster, but they require conditions that may occur only in sufficiently massive stars with particular compositions. The envelope and atmosphere matter because they determine how heat flows from the interior to the surface. An accreted envelope of light elements can be more transparent to heat than an iron-rich envelope, affecting the relationship between core temperature and surface temperature. Magnetic fields matter because they can make heat flow anisotropic, channeling heat along field lines and producing hotter polar regions. So cooling curves become one more kind of evidence. If you can estimate a neutron star's age and surface temperature, you can compare to models and infer something about mass, envelope composition, and internal neutrino processes. It is not a single clean measurement. It is a pattern match across many uncertainties, but it adds weight to certain models and undermines others. Now let's step back to rotation, because rotation is the second great energy reservoir after heat. Neutron stars are born rotating. The core of the progenitor star had angular momentum, and when it collapses from thousands of kilometers down to tens of kilometers, conservation of angular momentum spins it up dramatically, like an ice skater pulling in her arms. A neutron star can rotate many times per second. Millisecond pulsars rotate hundreds of times per second. Rotation is not free. It carries rotational energy, and that energy can be lost over time through electromagnetic radiation and particle winds driven by the magnetosphere. Pulsars spin down. Their periods increase gradually. This spin down is itself a tool. It can help estimate pulsar ages. It can reveal changes in torque that might relate to magnetospheric state changes. It can provide evidence for internal dynamics when the spin changes abruptly in glitches. But the most direct way rotation becomes evidence is through timing. The pulses are timestamps. When you measure them precisely, you can test gravity in binary systems, detect orbital decay due to gravitational wave emission, and even search for subtle disturbances. Pulsars have been used to indirectly confirm gravitational radiation through the orbital decay of binary systems, long before ground-based interferometers detected gravitational waves directly. So a neutron star is not just a dense object, it is an instrument. It is a rotating clock in a relativistic gravitational field. Now, to understand pulsars fully, we need the magnetosphere. A neutron star's magnetic field, combined with rotation, creates electric fields that can pull charges from the surface. Those charges populate the space around the star, creating a plasma environment threaded by magnetic field lines. In the simplest picture, field lines near the star are closed loops, and the plasma is forced to co-rotate with the star along those lines. But co-rotation cannot continue indefinitely, because at some distance, the co-rotation speed would exceed the speed of light. That distance defines the light cylinder, a cylindrical surface around the rotation axis where co-rotation would reach light speed. Inside the light cylinder, the magnetosphere can be closed and co-rotating. Beyond it, field lines open and particles can stream outward, forming winds and beams. In many models, the radiation we see, the pulses, is produced in regions where particles accelerate and emit along open field lines, with geometry and emission physics that vary among pulsar types. The details are still a lively research area. Different emission models place the origin of radio and high-energy beams in different locations, near the polar caps, in outer gaps, in current sheets. But the magnetospheric framework is robust, rotating magnetized plasma under relativistic conditions. NASA's Neutron Stars Are Weird article describes neutron stars as the strongest known magnets and notes that magnetars push the concept further. Magnetic fields another 1,000 times stronger than typical neutron stars. It also points out something that feels almost mythic but remains physical: starquakes. A magnetar's magnetic field can stress the crust. The crust is solid, but it is under enormous strain. When it yields, when it shifts, cracks, or rearranges, the magnetic field lines coupled to it can snap and reconfigure, releasing energy in bursts of X-rays and gamma rays. Some magnetar flares have been so intense that they have produced measurable effects in Earth's upper atmosphere, even from thousands of light years away. This is one of the few places where neutron star physics touches the Earth in a direct, measurable way. A distant crust fracture, a magnetic reconfiguration, and a wave of high-energy photons that changes the ionosphere. So we have three faces of the neutron star now: a cooling ember with a thin atmosphere forming a spectrum, a rotating lighthouse with pulses timed like a clock, a magnetic engine capable of sudden, violent flares. These faces are connected by the same interior, the same compactness, the same equation of state. Now we return to the central measurement problem, mass and radius. The mass-radius relation is the translation layer between microscopic physics and macroscopic observation. If you change the stiffness of the equation of state, how quickly pressure rises with density, you change the radius for a given mass and the maximum mass the star can support before collapsing. In the last decade, observations have put strong pressure on this space. The existence of neutron stars around two solar masses rules out many soft equations of state that would collapse too soon. Gravitational wave observations of neutron star mergers constrain tidal deformability, which depends on how easily the star deforms under tidal forces, again connected to radius and internal structure. These constraints do not yet point to a single equation of state. The field is still narrowing the possibilities, not finishing the story. But the pattern is clear. Radii for typical neutron stars seem to fall somewhere in the 10 to 14 kilometer range, depending on method and assumptions, with a trend toward tighter constraints as data improve. NICE's contribution is in providing radius constraints using X-ray timing and pulse profile modelling, particularly for millisecond pulsars with hotspots. And because this is a sleep story, we can let the process unfold slowly, like a careful reconstruction rather than a sudden reveal. Imagine a neutron star with a hotspot near a magnetic pole. The star rotates, the hotspot swings into view, brightens, swings out, dims. That's the simple lighthouse picture, but on a neutron star, 3 additional effects alter the pulse. First, light bending. The star's gravity curves the path of photons, letting an observer see more of the surface at once. This can keep a hotspot visible even when it is geometrically behind the limb in a flat space picture. Second, gravitational redshift. Photons lose energy climbing out of the gravitational field, shifting their spectrum. This affects how we interpret the observed temperature and emission. Third, special relativistic Doppler effects. If the star is spinning rapidly, the surface moves at a significant fraction of the speed of light, boosting emission when the hotspot moves towards the observer and dimming it when moving away, also affecting the shape of the pulse. Combine these effects with geometry, inclination angles, spot shapes, observer line of sight, and you get a pulse profile, a waveform. NICE measures that waveform in X-rays. It accumulates photon arrival times. It builds a profile over many rotations. Their models are fit to the data to infer likely ranges of mass and radius that produce the observed shape. It is not a single measurement. It is a statistical inference backed by physics. And because the physics includes general relativity, NICE is also, indirectly, a general relativity experiment. The fact that light bending makes it possible to see both polar caps under certain conditions is not a poetic flourish. It is one of the reasons the method works. At this point, the story could remain entirely in the realm of quiet measurement. Stars rotating, hotspots pulsing, instruments listening. But neutron stars have another way of revealing their interiors, one that happens only in the last moments of their lives as isolated objects. They merge. When 2 neutron stars orbit each other, they emit gravitational waves. The waves carry energy away, and the orbit shrinks. The stars spiral inward. Their orbital frequency increases. The gravitational waves rise in pitch and amplitude. This inspiral is not only a signal, it is a probe. As the stars approach, tidal forces deform them. The amount they deform depends on the internal stiffness of the stars, which depends on the equation of state. This deformation subtly changes the gravitational wave signal. It changes the phase evolution. It leaves fingerprints. When the stars finally merge, they can produce a short gamma-ray burst and a kilonova, an explosion powered by radioactive decay of heavy elements synthesized in neutron-rich ejecta. The 2017 multi-messenger event dramatically confirmed the connections among gravitational waves, gamma rays, and kilonova emission, and it established neutron-star mergers as sites of heavy element production for elements like gold and platinum. But tonight, we will focus on a narrower slice of that story, the magnetospheres just before the merger. Because the magnetosphere, normally a persistent structure around a pulsar, becomes something else when two neutron stars come close enough for their magnetic fields to interact. In NASA's research article on tangled magnetospheres, the team ran more than 100 simulations of merging magnetized neutron stars using the Pleiades supercomputer. They explored how different magnetic field configurations affect how electromagnetic energy leaves the system. They concentrated on the final moments, the last several milliseconds before the merger, because that is where everything changes quickly and where magnetic fields can reconnect, accelerate particles, and produce bursts of radiation. In their simulations, the magnetosphere behaves like a magnetic circuit that continually rewires itself as the stars orbit. Field lines connect, break, and reconnect. Currents surge through plasma, moving at nearly the speed of light. Rapidly varying fields accelerate particles. This is a striking description because it turns the magnetosphere from a vague aura into an engineered object, something with circuits and rewiring. It is still plasma physics, still electromagnetism, still general relativity setting the stage. But the language is right. It is dynamic, non-linear, and structured. The simulations highlight regions producing the highest energy light. In those regions, electrons can emit gamma rays through curvature radiation produced when charged particles follow curved trajectories along magnetic field lines. But here is the crucial twist, and it is the kind of twist neutron stars love. The brightest, highest energy gamma rays may not escape at all. In the presence of extremely strong magnetic fields, a gamma ray photon can convert into a particle pair, an electron and a positron. The highest energy gamma rays, with energies trillions of times greater than visible light, quickly convert to particles in the intense fields. They become trapped in a cycle of transformation between particles and radiation. Lower energy gamma rays, still extreme by human standards, with energies millions of times greater than visible light, can escape. The resulting particles can radiate at still lower energies, including X-rays. The emission varies rapidly and is highly directional, which means that what a distant observer sees depends strongly on perspective. This is the kind of result that feels technical and yet deeply intuitive once you accept the environment. Strong magnetic fields that can turn light into matter and matter back into light, in a plasma moving near the speed of light, in a gravitational field that is itself changing as two massive objects orbit and spiral inward. The significance is not only that we have a dramatic story. The significance is that this offers potential pre-merger electromagnetic signals, X-rays, and medium energy gamma rays that could be detected in the run-up to a merger, especially if gravitational wave observatories provide alerts and sky localization. In other words, the merger is not a single moment, it is a process with a lead-up, and the magnetosphere may glow before the collision, offering a new way to connect gravitational waves and electromagnetic observation. This is the newest edge of the case file, the part still being written. Now, with that modern edge in mind, we can relax back into the steady interior story again, because the merger does not replace the interior, it emphasizes it. Tidal deformability depends on crust and core stiffness. The ability of the magnetosphere to accelerate particles depends on field strengths and plasma behavior, which depend on the star's surface conditions and rotation. The fate of the remnant, whether it becomes a hypermassive neutron star for a time or collapses quickly to a black hole, depends on maximum mass and equation of state. Everything points back to the same central question: what is the pressure inside at a given density for the matter that exists there? So we return once more to the equation of state, but this time with a softer, more practical framing. Think of the equation of state as a rule of compressibility. If you add more mass and increase pressure, does the matter push back strongly or weakly? If it pushes back strongly, the star can support more mass and may have a larger radius for a given mass. If it pushes back weakly, the star compresses more, has a smaller radius, and reaches instability at a lower maximum mass. In general relativity, stability is subtle. There is a maximum mass for a given equation of state. Beyond that maximum, no stable neutron star exists. Collapse continues to a black hole. This means every neutron star is a negotiated truce between gravity and pressure, and the equation of state is the negotiated document. The TOV equation expresses hydrostatic balance in curved spacetime. It tells you how pressure must decline with radius to support the star. It accounts for the fact that energy density and pressure gravitate. It accounts for relativistic corrections that are not small. You do not need to solve the equation by hand to feel its implications. You only need to accept this. In a neutron star, pressure is not a local matter. It is part of the gravitational field. The deeper you go, the more pressure contributes to the star's own gravity, which makes the balance more severe. This is why neutron stars are not just dense, they are relativistic objects. It is also why observations that constrain compactness, mass divided by radius, are so valuable. They test the interplay of gravity and dense matter simultaneously. Now we can take a quiet inventory of how the universe lets us constrain these quantities. From pulsar timing in binaries, we get masses with remarkable precision. From X-ray timing and pulse profiles with NICER, we get constraints on radii and compactness. From gravitational waves in mergers, we get tidal deformability constraints and, indirectly, radius constraints. From thermal emission and spectral modelling, we get additional radius estimates, though with significant dependencies on distance and atmosphere composition. From cooling curves, we get hints about internal neutrino processes and envelope composition. Each method has uncertainties, but together they form a web, a triangulation, and the web is tightening. To keep our pace gentle, we'll move through 3 slow scenes that help the science settle into memory. The first scene is the surface as a place where light is formed. In the neutron star atmosphere, thermal photons scatter and absorb. The spectrum is shaped by the composition, hydrogen, helium, carbon, and by the magnetic field. A strong field changes atomic structure and opacities. It can make the atmosphere partially ionized in complex ways. It can even, in extreme cases, lead to a condensed surface, solid or liquid, where the atmosphere is reduced or altered. The practical consequence is simple. When you see a thermal spectrum, you are not seeing the core. You are seeing the atmosphere's translation of the core's heat into photons. If you misread that translation, you misread the radius. So neutron star atmospheres are not a footnote. They are a gatekeeper. The second scene is the crust, as a place where stress accumulates. The crust is solid, but it is not relaxed. It is under enormous gravitational pressure. It is tied to the magnetic field. Small movements can be explosive in their electromagnetic consequences, especially in magnetars. The crust can store elastic energy and release it in starquakes. It can respond to the evolution of magnetic fields. It can participate in glitches through interactions with superfluid components. And because the crust is where nuclear pasta may exist, it may also influence conductivity and magnetic field decay. So the crust is not just a shell, it is a dynamic interface between the star's interior physics and its electromagnetic behaviour. The third scene is the magnetosphere as a place where particles become light. In a magnetosphere, charges move along magnetic field lines. Electric fields accelerate them. Radiation emerges through curvature radiation and other processes. The geometry of field lines and the distribution of plasma determine what beams exist and where they point. This is where a neutron star becomes a lighthouse, and in mergers it becomes a rapidly rewiring circuit. These scenes are different, but they are linked by the same compact object. Now we can take one more careful step into the interior, focusing on a few anchor points that are both hard science and sleep-friendly. Anchor point 1, neutron-drip. It happens at densities around a few times 10 to the 11 grams per cubic centimetre. Below it, neutrons are bound in nuclei. Above it, neutrons are free to exist outside nuclei. This is not a metaphor, it is an energy condition. Once the chemical potential makes it energetically favourable, neutrons become unbound. The matter changes character. Anchor point 2, the inner crust's superfluid. At the densities and temperatures of a neutron star crust, neutrons can pair up and behave collectively, producing superfluid behaviour. This affects heat capacity and heat transport, and plays a role in certain neutrino emission mechanisms during cooling. It also offers a plausible reservoir of angular momentum that can couple and decouple from the crust, explaining sudden spin changes. Anchor, point 3, nuclear saturation density. Around a few times 10 to the 14 grams per cubic centimetre, matter transitions toward uniform nuclear matter. This is the boundary region where models change from lattice-based descriptions to core descriptions. Anchor point 4, the core's uncertainty. The outer core is likely a dense fluid of neutrons with some protons and electrons and possibly muons in beta equilibrium. Superfluidity and superconductivity may occur. The inner core, at higher densities, may include additional degrees of freedom, but the evidence is not decisive. What we can say with confidence is that whatever is there must produce an equation of state stiff enough to support the observed maximum masses. These anchors keep us honest. They prevent the story from drifting into speculative imagery. They keep the weird grounded in density thresholds and equilibrium conditions. Now, because this is a sleep episode, we will allow ourselves a long, slow loop through the same story again, but from a different angle. A guided tour that begins not with the interior, but with the measurements, and then asks what interior structure could produce them. Imagine you are an observer with 3 tools. A radio telescope that can time pulses, an X-ray telescope that can measure pulse profiles and spectra, a gravitational wave detector that can hear inspirals. From radio timing, you learn that a neutron star's rotation is extraordinarily stable. You learn that pulses arrive with clock-like regularity. In some cases, you learn that the star is in a binary, and the orbit is decaying in a way consistent with gravitational wave emission. You learn masses with great precision. From X-rays, you learn that the star emits thermal radiation and sometimes has hotspots that produce periodic modulation. You measure spectra shaped by atmospheres and fields. You measure pulse profiles shaped by relativity and geometry. From gravitational waves, you learn that when two neutron stars merge, the inspiral encodes information about tidal deformability and thus about internal stiffness. Now you ask, what kind of object produces all three? A small object with a hard surface, because hotspots and surface emission require a surface. A dense object with strong gravity, because light bending and redshift are observed, and because the orbital dynamics in binaries are relativistic. A magnetized object, because beams and magnetospheres exist. A strongly supported object, because it does not collapse immediately under its own gravity. It is stable, sometimes up to 2 solar masses. This is the neutron star. And then you ask, what kind of matter supports it? Degenerate matter, because thermal pressure alone would not be enough. Nuclear matter, because densities are near or above nuclear density. Matter in beta equilibrium, because weak interactions set the composition. Possibly superfluid and superconducting matter, because quantum pairing at high density is plausible, and because it helps explain certain observational behaviours. This is the interior picture, inferred rather than seen. And now you let the equation of state be the connecting link, a function that tells you how pressure rises with density for that matter. The equation of state is the piece we want most. Now we can speak plainly about what makes neutron stars weird without losing the physics. They are weird because they are both astronomical and nuclear. They are weird because they have a crust that is, in a sense, a gigantic crystal of neutron-rich nuclei, and a core that is, in a sense, a gigantic atomic nucleus with additional complications. They are weird because they can spin hundreds of times per second and remain stable, and because their pulses can outregulate many human-built clocks. They are weird because their magnetic fields can distort atoms, channel heat, and power bursts that ripple all the way to Earth. They are weird because they turn light into matter in their magnetospheres, and matter back into light, and because in mergers they may produce high-energy photons that cannot escape their own magnetic traps. And they are weird because they are visible enough to study, but not transparent enough to fully understand. They are the closest thing we have to a dense matter laboratory, and yet they keep their deepest secrets inside. At this point, the temptation is to sprint, to list all the phenomena: glitches, bursts, accretion, jets, gravitational waves, Kilonova, gamma-ray bursts, neutrino cooling, superfluid vortices, R modes. But tonight we will move slower. We will choose a few phenomena and let them breathe. Let's choose accretion because it is a simple engine that reveals a lot. In an X-ray binary, a neutron star can strip gas from a companion. The gas forms an accretion disk because it has angular momentum. It cannot fall straight in. Friction and turbulence in the disk convert gravitational potential energy into heat, and the gas glows in X-rays. Near the neutron star, magnetic fields can channel the flow onto hotspots near magnetic poles. The impact releases tremendous energy because the gravitational potential is so deep. A small amount of mass can produce a large amount of radiation. This process not only makes neutron stars bright and observable, it also deposits material onto the surface. It changes the envelope composition. It can bury magnetic fields or reshape surface layers. It can heat the crust, and when accretion stops, the crust cools. offering a way to study thermal transport and crust physics. This is a beautiful pattern. An external process, accretion, creates an internal experiment, heating and cooling, whose relaxation tells you about conductivity, heat capacity, and perhaps the role of unusual phases like pasta. Now let's choose glitches, because they connect rotation to interior superfluidity. Pulsars generally spin down over time, but some pulsars occasionally exhibit sudden increases in rotation rate, glitches. The changes are small in absolute terms, but precise and measurable in timing. One broad class of models attributes glitches to interactions between a superfluid component inside the star and the crust. In a superfluid, angular momentum is carried by quantized vortices. Those vortices can pin to the crust lattice or to defects. If vortices suddenly unpin and move, angular momentum can transfer, changing the crust's rotation rate. The details of glitch models are complex and still debated, but the essential point is that glitches offer evidence that the star contains superfluid components coupled imperfectly to the crust. Again, the interior leaves fingerprints on the outside. Now let's choose magnetar bursts, because they connect magnetic field evolution to crust mechanics. A magnetar's magnetic field can be so strong that it stores enormous energy. As the field evolves, it can stress the crust. The crust resists up to a point. Then it yields. When it yields, the magnetic field can reconfigure, releasing energy as high-energy radiation. This picture is supported by the observed behaviors, bursts and flares in X-rays and gamma rays, often with quasi-periodic oscillations and other features that suggest crust and magnetosphere dynamics. Even without every detail nailed down, the broad energy budget and coupling mechanisms are consistent with this magnetic crustal interaction model. Now we choose one final phenomenon, the merger magnetosphere, because it connects everything: fields, plasma, relativity, and observation in a modern, predictive way. In the NASA simulations, the magnetosphere rewires like a circuit. This rewiring accelerates particles and generates high-energy radiation. The highest energy gamma rays may be trapped by pair creation, converting into electrons and positrons. Lower energy gamma rays and X-rays may escape, potentially providing detectable pre-merger signals. This matters because it suggests that neutron-star mergers may be heralded not only by gravitational waves, but also by electromagnetic precursors, depending on magnetic configuration and observer geometry. It also matters because it expands the multi-messenger idea. Not just light and gravitational waves after a merger, but light and gravitational waves before it. Now we will let the episode drift into a long, calm deepening, revisiting the interior with one more layer of detail, but always anchored to hard science. In the outer crust, the pressure is largely provided by electrons. Electrons are degenerate, and at sufficiently high densities, they become relativistic. The nuclei form a Coulomb lattice. The composition is determined by minimizing energy. Which nuclei have the best binding energy per nucleon under the given pressure and electron chemical potential. As you go deeper, the equilibrium nucleus becomes heavier and more neutron-rich. The electron fraction changes. At some depths, electron capture changes nuclei rapidly. At neutron-drip, free neutrons appear. From this point on, pressure includes contributions from degenerate neutrons as well as electrons. The nuclei remain, but their environment is now soaked in neutrons. The free neutrons can form a superfluid. The lattice remains solid. The electrons remain degenerate. This is an unusual mixture, a solid lattice embedded in a superfluid and an electron sea. At higher densities, nuclei deform. Pasta may appear. Then, at the crust-core transition, the lattice disappears and matter becomes uniform. In the core, nucleons and leptons form a dense fluid. Neutrons dominate. Protons and electrons maintain charge neutrality. Beta equilibrium sets the relative fractions. At high enough densities, additional particles may appear, but we treat that as an open file rather than a solved one. Throughout all of this, temperature matters, but in a specific way. The star's temperature is high in absolute terms compared to human experience, millions of degrees for much of its life at the surface, higher inside. But in terms of the Fermi energies of degenerate particles, it can be relatively low. This is why degeneracy and quantum effects dominate. So even though a neutron star can be hot, it can still behave like a quantum solid and a quantum fluid. Now, we turn back toward observation one last time, because this is where the story becomes reassuring. In science, reassurance often comes from redundancy. We have multiple methods pointing to similar scales. The size scale, roughly city-sized radii, around 10 to 14 kilometers. The mass scale, around 1 to 2 solar masses, with known cases near 2. The density scale, near nuclear density in the interior. The gravitational scale, compactness large enough that relativity matters strongly. The magnetic scale, fields billions to trillions of times Earth's, sometimes much higher. The rotation scale, up to hundreds of rotations per second, with the fastest known pulsar spinning 43,000 times per minute. These numbers are not random, they hang together, they form a coherent picture. That coherence is itself evidence. It is what makes neutron star science feel less like a set of weird facts, and more like a single physical object viewed from different angles. Now, to bring everything gently toward the end, we will do one final calm sweep that ties the entire episode into one continuous arc, from birth to measurement to merger, without rushing. A massive star lives. It fuses light elements into heavier ones. It reaches iron. The core grows. Degeneracy pressure carries the load until it cannot. Collapse begins. Neutrinos carry away energy. At nuclear, neutrinos carry away energy. At nuclear density, matter stiffens. The core bounces. A shock wave forms. A supernova explodes under conditions still studied and modelled. A compact remnant remains. That remnant is born hot and cooling. Neutrinos carry away energy from within. Photons carry away energy from the surface. The star's surface temperature stays high enough to emit X-rays. The star is small, dense, and relativistic. Light leaving the surface is redshifted. Its paths are bent. Time near the surface is not the same as time far away. The star may rotate rapidly. Its magnetic field threads the surrounding space. Charges populate a magnetosphere. Beams form. Pulses sweep across the sky. Astronomers detect the pulses. They time them. They measure orbits. They infer masses. They test gravity. In X-rays, astronomers measure hotspots and pulse profiles. They model light bending and Doppler effects. They infer radii and compactness. In gravitational waves, astronomers detect inspirals and mergers. They infer tidal deformability. They constrain the stiffness of dense matter. In the last moments of a neutron-star binary, magnetospheres interact, fields reconnect, circuits rewire, particles accelerate. Light is produced at extreme energies, some trapped by pair creation, some escaping at lower energies. Gravitational waves and light together tell a richer story than either messenger alone. And through all of it, the equation of state sits quietly, the document we keep trying to read. What is pressure at a given density? What is the radius at a given mass? What is the maximum mass before collapse? What phases of matter exist in the crust and core? What does nuclear matter become when you compress it beyond what nuclei can hold? We do not yet have every answer, but we have enough answers to make neutron stars more than a list of oddities. We have enough to treat them as a coherent physical object, one that can be studied, constrained, and slowly understood. In my office, the folder is still open. The desk lamp still throws a small pool of light across the page, and the page is filled with numbers that refuse to be poetic unless they are true. 10 kilometers, 2 solar masses, 1 trillion kilograms in a sugar cube, milliseconds, X-rays, a magnetic field strong enough to change the way atoms prefer to exist. Outside the window, the sky is the same dark pane, and the distance is still patient. But the distance feels less empty when you know that somewhere in it, a city-sized sphere can spin like a blade, bend light like glass, and keep time like a clock, all while holding matter in arrangements we are still learning how to name. And with that, we close the case file, quietly, carefully, on neutron stars.